All right, to finish up this section on simple harmonic motion, I'd like to look just a little bit at another form of the angular momentum expression. You may recall from before that angular momentum can be written as I omega. But there is an alternative form for a point mass that is useful in some situations. And so I'd like to look at that example. And that's also relevant to a couple of the lab exercises that you're doing this week. So if we write the moment of inertia for a point mass as mr squared, we might write omega as v tangential over r. For here, this is v tangential, and this is r for a mass that's going round and round in a circle. Then this is equal to mvr. Okay, so that's kind of like linear momentum multiplied by the radius of that linear momentum, and that's another way of expressing angular momentum. But in reality here, for a problem that's a rigid body, the velocity is always perpendicular to r. So really, we should, in general, write this as mv times r perpendicular, where r perpendicular is what we could call our lever arm distance. And we also looked at this before with torque, with r cross f. And so we can rewrite then the angular momentum expression as a vector cross product of the radius vector and the momentum vector, the tangential momentum vector. Okay, and so let's take a look at an example of how that could work. Let's say that we want the angular momentum about this point P. Okay, and so we have a mass moving with a velocity v along this horizontal axis. Then our radius vector at different points along this horizontal path will just be a vector that points from P and connects in with the moving mass. But as this thing moves, there is one value for r that remains constant, and that's the perpendicular part of r. So in other words, here we have a parallel part for r and a perpendicular part for r. But the perpendicular part is this part here. Okay, and so if we just extend this momentum vector and draw a line that goes from the point P to where it intersects that momentum vector at a 90-degree angle, this gives us our r perpendicular. That's r sine theta, where theta is the angle between v and r in general. Okay, and so if this is r, then here I'm just moving the r vector so that it has tail that connects in with the tail of v. Then r perpendicular is going to be this part here. So this will be r perpendicular, which is r sine theta. But that's just the same value as this value here, which is the r sine 90. Okay? And so this distance and that distance are the same value. Okay? And similarly over here, the r perpendicular is just the perpendicular part of r in this L equals r cross mv. So what that shows us here is that the angular momentum is constant as the mass moves across in this horizontal direction, and that the r perpendicular is the minimum distance from the point P to the point that connects in with the mass when the angle between r and mv is 90 degrees. Now we can do a vector cross product by curling our fingers from r in the direction of v, and that gives us an angular momentum vector that's perpendicular to the plane that contains r and mv, and in this case that would point out of the board. We can compare that with the direction for omega. Remember that the way that I had you figure out the direction for omega again, which is the spin axis, is by curling your right hand in the direction of omega. And then the direction that your thumb points is the direction of the angular momentum. So the angular momentum in either case, since this thing tends to have a sense which would be like a counterclockwise rotation, just like this one, would be to have an L value that points out, just as is the case here, where it's R cross MV has an L that points out. Now, you may be wondering, though, why am I trying to figure out the angular momentum about some abstract point, like P here? I mean, what's the purpose of that? The answer is, let's say that there's a reason for thinking of that as being our center of spin. For example, maybe we've got a long rod that has a length L that's equal to R perpendicular. Okay? And let's say that we secure that rod about this P point here, which now becomes our pivot point. Then, if this mass comes in and smashes into that rod at this point, then there's going to be a certain angular momentum that's equal to mv times r perpendicular, or in this case, that angular momentum would be mvl, where L is the length of the stick. So here's L, and so here is our mass. It comes in and it hits, but just before it hits, the angular momentum is mvl. Then what is it afterward? Well, L afterward is going to be equal to I times omega. Okay, so, but this is going to be the omega for this mass, which is now rotating up to some maximum angle theta. Okay, and so the I value now, once these things are in contact and it's rotating about this point P, is going to be equal to, well, if we have this mass here is little m, and the mass of the rod is big M, then I would be equal to little m times L squared plus, and then if we rotate this rod about its end, using the parallel axis theorem, we get 1/3 m L squared. Okay, so that is our moment of inertia. And then we can say that omega, in this case, is equal to V over R. Okay, and so if we write that in now for L final, we get little m times L squared plus 1/3 big M times L squared times V over, and then R is just going to be L. This is just at the moment after it's struck. So this is L final. This is an inelastic collision, and the mass sticks to the rod, just like in the lab simulation. Okay? And so this gives us, by using conservation of angular momentum, we can now set L initial equal to L final, because there's no external torques acting. All of the forces are internal to the system, which is the mass striking that rod. Okay, and so we get then little m times V. Now this is V final. This is V initial. So this is going to be little m times V initial times L equals little m times L squared plus 1/3 big M times L squared times V final over L. And so then one factor of L will cancel here. A second factor of L will cancel there as we go through. And this gives us a final result of little m times V naught equals little m plus 1/3 times big M times V final, where this is the velocity of the mass just before the collision. And this is the velocity of the mass and also the end of the stick just after the collision. So this then gives us a condition on the initial velocity. Okay, so now let's say that this mass swings up to some height that is associated with an angle of 30 degrees. Okay, so after the collision takes place, we can use conservation of energy. So using conservation of angular momentum during the collision, and then after the collision, the system swings up to 30 degrees. And then it goes into simple harmonic motion. So this is what connects in with simple harmonic motion, is we have this mass, comes in, hits this long rod, starts it swinging. We have a relationship between the velocities at the end of the stick, just before and after the collision. And now we can also use the fact that the final potential energy equals the initial kinetic energy. Okay, so this is just conservation of energy for this problem, where the initial kinetic energy is the kinetic energy of rotation just before the collision. So that would be 1/2 I times omega squared. Okay? And then after the collision, what we would have is, well, this thing is going to swing up, so this mass here is going to move up that amount. So that would be little mg times L minus L cosine theta. Okay, because this whole thing is L. And so this height here is L minus L cosine theta. So we have mg times L minus L cosine theta will give us the height that this mass moves up, plus the height of the center of mass. How high does the center of mass move? Well, it's going to move from L over 2 to L over 2 minus L over 2 cosine theta. Okay, and so the height that the mass moves in is going to be big M g times L over 2 times 1 minus cosine theta. Okay, so this then is the potential energy final, which is basically the movement of the center of mass of the beam, which is this term, multiplied by little mg. So this is L over 2. This is L over 2 cosine theta. And so this term here then is L over 2 minus L over 2 cosine theta. So that's what we have here. mg times L over 2 minus mg times L over 2 cosine theta. Okay, so that's our change in potential. All right, so from the lab then, you can figure out what these two terms are. Then you can go in and you can figure out what omega has to be after the collision, using the expression for I that I wrote here for you. Then you can write omega as V over R, and you can set up this kind of an equation for the conservation of angular momentum before and after the collision. And then from that, you should be able to get the initial velocity. And so that's what I ask you to do in that lab simulation. Okay? And so hopefully this gives you the information that you need in order to do a good job with that. Okay, so let me know if you have any questions regarding this, I will be having a Zoom office hour this week, and so I'm going to announce that later today.